Welcome to Study Loop.
So in this problem, we have a loop that's built from this metal bar on two railings. So there's a battery supplying 12 volts. There's a switch. And this bar has a mass of 0.90 kilograms, and it supplies a resistance of 5 ohms. It has a length of 0.36 meters. And through the entire area, there's a magnetic field of 1.5 Teslas. So first, what we want to do is determine the graph of the speed as a function of time. So what's the speed of this bar as a function of time? First question to think about is, why would it even move at all? So when this switch closes, there's going to be a current. So suppose the switch closes, there's going to be a current like this. So that current is going to flow clockwise. But if you have a current carrying wire in a magnetic field, it feels a force. And that force is ILB when the current and magnetic fields are perpendicular. And you can see that they are because the current is straight down and the magnetic field is straight out. What's the formula for this current? Well, let's call this the battery current. So the battery current comes from Ohm's law. So it's just the battery voltage divided by R. So that current leads to this kind of force, which pushes the bar this way. But once the bar starts moving, the area subtended by the circuit, this area right here, increases, right? Because the bar is going this way, so the area is getting bigger and bigger. But if the area is getting bigger, then the flux is changing. And if the flux is changing, there's an induced current. So there's another current coming from Faraday's law. So first of all, we have the induced EMF is the number of turns times the rate of change of flux. There's only one turn, so N is 1. And the magnetic field is constant, so this is just going to be B times dA dt. Right, so I just use the fact that flux is equal to magnetic field times area. What's the area? Well, the area of the circuit is the length times x, where let's say x is this distance. So we weren't actually given that in the problem, but it doesn't matter because the length of the bar isn't changing. So this is just BL dx dt. And dx dt is exactly what we want. It's the speed. So this is BLV. And then from Ohm's law, this is equal to IR. So the Faraday, let's call it Faraday current, is BLV over R. So remember, the battery current was clockwise. What direction is the Faraday current? Well, the area is increasing, right? The area is getting bigger. So therefore, the flux is getting bigger. If the flux is getting bigger, the induced magnetic field will try to cancel that by pointing out of the page, right? It'll try and cancel this. And therefore, the right-hand rule provides that this Faraday current actually flows counterclockwise. So they cancel. So the total current is actually the difference between those. It's the battery current minus the Faraday current. Okay, so this is going to go into there. So we have F equals MA equals ILB, which equals battery voltage minus BLV over R times LB. And we can solve for the acceleration, which is then LB over MR times the battery voltage minus BLV. And I'm just going to do one more line of algebra and factor out the BL. So the final equation is going to be L squared B squared over MR times battery voltage divided by LB minus V. So now would be actually a good time to substitute in some numbers just so we don't have to push these around so much. And we know all of these quantities, right? We know the battery voltage, we know the length, we know the magnetic field, we know the mass, and we know the resistance. So when you substitute all those numbers in, what you'll find is that the acceleration is 1 over 15 seconds times 22 meters per second minus v. So you can just see that it looks a lot nicer when you make that simplification. Now we can use the fact that the acceleration is the rate of change of the velocity. So the acceleration is dv dt. Therefore, we have a differential equation. So dv dt is 1 over 15 seconds times 22 meters per second minus v, with the initial condition that v of 0 is 0, right? The initial velocity is 0. So there's a few ways to solve this. You can use separation of variables. It's a linear equation, so you can just sort of look up the solution. But to save the work of doing that kind of algebra, I'll just simply tell you the answer. It's going to be 22 meters per second times 1 minus e to the negative t over 15 seconds. So there's the formula for the velocity as a function of time. Again, that comes from just solving this differential equation, which can be done by separation of variables or something else. Now we can finally sketch the graph. So as a function of time, this is an exponentially increasing function. It looks exactly like the formula for a charging capacitor. So it looks like this, where this is 22 meters per second. Okay, so that's the formula. So that tells us the shape of the graph. Now, how about the acceleration? Well, now that we have a formula for the acceleration, it's very easy to calculate this because we can just substitute v equals 0, because this is at t equals 0, the velocity is 0. So a at t equals 0 is just 22 meters per second divided by 15 seconds, which should give you 1.47 meters per second squared. And then for C, we just substitute V equals 2 meters per second. So this is A when V equals 2 meters per second, which is 1 over 15 seconds times 22 meters per second minus 2 meters per second, which is 1.3 meters per second squared. And then D asks, what's the terminal velocity? Well, the terminal velocity is just when the acceleration is 0, right? So if the acceleration is 0, this means that 1 over 15 seconds is 22 meters per second minus v. And that immediately implies that the terminal velocity is just 22 meters per second. And that is the full solution to the problem.